Let's now look at the reflection of a sine wave at a fixed end. Here's the wave machine with a sine wave travelling along meeting the fixed end. In the cartoon, we can also show the inverted wave appearing magically from beyond the fixed end. What we notice is that for a little while the wave is simultaneously travelling to the right and its inversion is travelling to the left, we have a standing wave, a wave in which the pattern is not going anywhere. Notice that there are points in the standing wave where there are no motion and points between them where the motion is a maximum. What sort of wavelengths can produce standing waves on a string? Well, if there's only one fixed end, then any wavelength can lead to a standing wave. If we have two fixed ends, we limit the allowed wavelengths. Let's look at a musical instrument. It's tempting to say fixed end at the nut and fixed end at the bridge. This, of course, is only an approximation. The whole point of the box of the guitar here is that a vibrating string causes a tiny vibration in the bridge. That causes a vibration in the belly of the guitar and also to the air contained inside the body of the guitar. And that's how the sound gets from the vibration of the string, vibration of the bridge, vibration of the belly, out into the vibration of the air in the sound wave produced by the instrument. But let's make the very good approximation that the string is fixed at this end and at that end. An infinitely long medium can support standing waves of any wavelength. Strings, however, are fixed at both ends. If we call the vibrating length L, then L must fit exactly n half wavelengths where n is an integer. The string can therefore resonate at a set of discrete wavelengths, lambda n equals 2L over n. We know how the wave speed v in a uniform string depends on the tension T and the mass per unit length mu. The frequency is the wave speed divided by the wavelength, so we can write this expression for the set of resonant frequencies. The animation shows some of these resonant standing waves, which we call modes of vibration. Their frequencies are called the harmonic series, for reasons that we'll hear later. We can see this in a rope where the vibrations are slow enough to see. I keep the tension constant and excite the wave with different frequencies, and I see that there are standing waves here with a frequency F1, with twice that frequency, with 3 times that frequency, and with 4 times that frequency. All of these standing waves are what we call resonances of the string. A resonance is the capacity of some system to store energy at a particular frequency. This string can store mechanical energy at a frequency F1, or at 2F1, or at 3F1, 4F1, so forth.